In section 6.7, we begin to analyze kinetic friction. Our objectives here are to redefine the work energy theorem to include a term that will account for friction and energy transferred to heat. We want to use this new version of the theorem to solve energy problems involving friction. Now, based off of our understanding of the last sections, we now know that total energy must be conserved. So any change in the energy in a system has to be the result of some sort of transfer. It might be work going in and out, it could be heat, it could be a change in the kinetic energy. What we're going to look at is solving some problems that involve friction, and we want to use energy considerations to get to our solutions. In order to do this, we have to modify the work energy theorem to include a constant frictional force on the object. Like we said in the last section, we could have an object that is undergoing some sort of an experience where it is increasing its temperature, not just its speed. So when we look at our old work energy theorem that only accounted for a change in the object's speed, it was a shortcoming in doing that. And we really have to be able to express how an object might be gaining or losing energy based off of frictional forces and the heat transfers that occur with them. So since we know that friction transforms kinetic energy in a system into internal energy, we can think of the work done by friction as the work that increases the internal energy. Since work is a force multiplied by a displacement, the work done by friction would naturally be that force of friction multiplied by the displacement that the object moves through. Now again, this amount of work is a change in energy. And specifically, when you look at work done by friction, the kind of energy that it changes is the internal energy. Basically, heat is going to be developed as you have a frictional force acting on an object. So in a system where friction acts alone, the increase in the internal energy would equal the decrease in the kinetic energy. When we want to simplify and rewrite our work energy theorem entirely, we can summarize the new work energy theorem this way, that these changes in kinetic energy can result from the work done by other forces as well as work that's sort of sucked out of the system by friction and has now gone into an internal energy. Let's now try some problems based off of this understanding. We have a block that is a 6 kilogram block initially at rest on a surface. It's going to be pulled to the right by a force of 12 newtons, and the coefficient of friction between the surfaces is going to be a coefficient of 0.15. We want to find the speed of the block after it has moved through a 3-meter displacement. Now remember, we did this problem just a couple of sections back, and we found that we were right around 3.5 meters per second as the velocity that this block would be moving through. But when we did this problem in the past, we did this problem without accounting for friction. Right now, we're going to take that frictional force into account and see how fast the block would be moving while accounting for the fact that friction will exist between the surfaces. Now, the way that I like to think through these problems is to think of it as the amount of work that's done on the object has gone into the change in the energy. Basically, if I sum up all the transfers of energy or all the work that's being done, that is going to equal the change in the total energy of my system. In this case, work is being done by this outside force. I have the 12 newtons that is acting across a 3-meter displacement. And the energy of this system is now going to change because of that work being done. I know that I'm going to change the kinetic energy of my block, and I also know that I'm going to change the temperature of the block as it slides across this frictional surface. So work is going into speeding the block up and warming it up a little bit. As I go through and solve this, I can look at my change in kinetic energy as being 1/2 the mass times the final velocity squared. And as the change in kinetic energy, it should be minus the initial 1/2 the mass times the initial velocity squared. And I also have this internal energy piece. This entire piece is going to go to 0 because it did not have any initial kinetic energy. So half of 6 is 3, my final velocity squared. And as I look at what has now gone into heating this block up, it is that frictional force multiplied by a displacement, where in this case, that frictional force is going to be the friction being mu times the normal force. Because it's on a horizontal surface, the normal force should just be the mass times gravity multiplied by the displacement. As I plug these values in, Vf should really be my only variable that I don't know. I know that mu is 0.15, the mass is 6, gravity is 9.8, and the displacement that the object is moving through is the 3-meter displacement. If you want to take a second and pause the video, you can solve for this final velocity on your own as well. Isolate V sub f, and you'd find that in this case, our final velocity comes out to be about 1.78 meters per second. This makes sense because when we did this problem without friction, the final velocity was close to 3.5 meters per second. We can see that our velocity here is going to be less. In this case, because of this resistive frictional force working against the block as it slides across the surface, we are now going to result in having a lower final velocity since friction is working against us and slowing the object down a bit. Let's look at the second question. The second question asks you to say what happens if this force is actually provided at an angle instead. What if we didn't pull at a horizontal 12 newtons, but instead we pulled with that 12 newtons at some sort of an angle theta? In this case, this would change the problem just a bit. And now we would look at the force acting at some sort of an angle like this instead, at some value of theta. Now, if we want to look for maximum speed, you might initially think, well, theta should equal 0 if we're looking for maximum speed. Basically, pull across in the direction of motion, put all of your force in that direction, and you'll maximize the speed of the block. What we're not recognizing in doing that is the fact that by applying this force at an angle, we're lifting up on the block a little bit. There's going to be a component of this force that is now lifting the block off of the surface, which is now going to reduce the frictional force that's going to be acting. With less friction, you can now get the block moving at a faster velocity. Let's begin by analyzing some of these forces. We know that we have the component of the 12 Newton force in an upward direction being a 12 sine of the angle theta, and the component of the force pulling it across the surface is now the 12 cosine of the angle theta. We have the mg of the block pulling down, and when we sum up the forces in the y direction, we'd find that the sum of the forces in y is going to be our mg pulling down and our 12 sine of theta pulling up, as well as our normal force from the surface in an upward direction. Now, in the y direction, the sum of these forces should equal 0. Our block is not accelerating up or down off of the surface at all. What this means is that when we sum up these forces and solve for the normal force, our normal force should be equal to our mg minus this 12 sine of theta. This is important because we're going to utilize this normal force while we're looking for that force of friction. Again, this work of pulling on the block has gone into a change in the kinetic energy, increasing K, as well as increasing the internal energy. Now we're going to try to get K all by itself on one side over here. So we will write this as K equal to the work minus the internal energy. Or basically, we want to say that the kinetic energy is going to be equal to the work done by the pull, which is now going to be our force of 12, our displacement of 3, multiplied then by the cosine of the angle theta. Basically, this piece of the force is actually pulling the block in the direction of the displacement, minus the internal energy. Well, that internal energy is going to be the work done by friction, or mu times the normal force of mg minus 12 sine theta multiplied by its displacement. Now, the interesting thing about this is that when we want to maximize the kinetic energy, which is basically what this last question is asking you, what angle do you want to pull at so that you maximize your speed? Maximizing your speed is really maximizing your kinetic energy. And if you remember from your calc class, if you want to maximize or minimize something, you basically want to take the derivative of that function with respect to your given variable. In this case, we want to take the derivative of the kinetic energy function with respect to theta. Now, as we do that, we want to essentially take the derivative of each piece. So the derivative of this piece here, with respect to theta, we'd leave the constants out front. The derivative of cosine is a negative sine of theta. Over here again, we'll leave the constants out front. The derivative of mg, both being constants, is just going to be a 0. And the derivative of the sine of theta, again, is going to be a cosine of theta. And we'll leave the constants again out front. So ultimately, what we have here is a negative fd sine of theta. And really, instead of the 12, we could write this as an f if we wanted to. And then we have a minus, a negative, so we'll turn that into a positive. And we have the mu, the fd, and the cosine of theta. And when we take this derivative and wanting to maximize this, we want to take the derivative and set it equal to 0. So ultimately, as we look at this equation, we could cancel out the fd's or divide by that on both sides, essentially, leaving us with this mu cosine of theta minus a sine of theta that's going to be set equal to 0. When we move these things around just a bit, we would have the mu cosine of theta equal to the sine of theta. We could then divide by cosine so that mu is equal to sine over cosine, or the tangent of the angle, theta. And we could then plug our value of mu in, where mu was our 0.15, and set that equal to the tangent of theta. So when we actually solve then for theta as the variable that we were looking for here, with a mu value of 0.15, the theta that is going to maximize your kinetic energy is going to be an angle of just over 8.5 degrees. So at that value, you would maximize the speed of your object.